Hi, I'm Andrew Baird, and I did my project on Stokes flow. So basically what Stokes flow is fluid flow with very low Reynolds numbers. And you can see, based on this slide, the consequences of that. The equation for Navier-Stokes simplifies down quite a bit. So you can see on the slide, it's a non-dimensionalized version of Navier-Stokes equation. I got that from one of my references. And you can see how it simplifies when the Reynolds number on the left goes almost to 0, and you can get rid of that whole left-hand term. It simplifies to what you see below. So this simplified version of the Navier-Stokes equation is simply called the Stokes equation. And some results of the Stokes equation is that the flow will be laminar regardless of the shape of whatever the shape is. There will be no eddies or turbulence whatsoever because the Reynolds number is so low. Also, because there are no time derivatives in this equation, it results in something called reciprocal motion. So I've included some quotes from my references that describe what reciprocal motion is. It's a pattern of motion that's the same whether slow or fast, whether forward or backwards. So if you change the shape of a fluid, it will generate a motion. When the shape is changed back to its original configuration with the exact reverse sequence, no matter how fast or slow, the body is moved back to its initial position. So this means if you put like a dye or something in the fluid and you move the fluid and then you move it back, whatever was in the fluid at the beginning will move back to its exact same position at the end of that movement. So what I did to show or test this phenomenon of Stokes flow is I designed an experiment where I filled a bowl with Karo syrup or corn syrup, which has a very high viscosity. I placed dye in the syrup, and then I rotated the syrup slowly with like a separate bowl I put in there. You'll see how it works in the video that will come up next. So this slow rotation led to a low fluid velocity, and the high viscosity and low velocity resulted in a low Reynolds number, which resulted in Stokes flow. So when you rotate the dye and then reverse the flow, the dye will move and then go back to its original position it was in at the beginning. So that experiment is coming up right now. Now I'll rotate the inner bowl, and you'll see the fluid rotating around. You can see it's rotated like that. So now it's been rotated, and if I rotate it back, it should go back to the starting position. See, it's no longer over there. It's only over here because I rotated it back. So you can see in that video that some of the dye kind of stayed on the top of the syrup, and then some of it actually was embedded in the syrup. And the dye that was on the top didn't exactly follow Stokes flow. Once I moved it, it didn't really move back. But the dye that was embedded in the syrup, you can see it did a very good job. It moved, it was like twisted and it was in torsion and whatever, and then when I twisted it back, it moved right back to its original position. You can see an example of this, much better examples and much more controlled experiments if you search it on YouTube. But that's what I did, and I hope you liked my presentation. And I have references at the end here. So.